All right, real quick, the last thing I need to talk about is some wave behaviors. Not all. These are specifically things that a wave can do when it strikes a barrier. We got all these pictures here, and sometimes, actually, often more than one of these happens simultaneously. There are four of them: reflection, refraction, diffraction, and absorption. There are going to be some other things we talk about when we get to sound and light, but these four things, I want to just briefly go over them. Most of them you understand and have heard of before. First one is reflection. You can see the picture up here. It's real simple. It's when a wave bounces off of something and goes in a new direction. Now, I want to remind you, this entire section is with all waves, like all of them. Light waves, sound waves, water waves, waves in a string. All waves can reflect. They can bounce off and go in a new direction. And the wave that reflects is important to know that it's exactly like the original. The same size, the same frequency, the same everything. So that's why, in terms of light, when you look at yourself in a mirror, which is one of the examples here, the color of your shirt, if you're wearing a red shirt, that means there are red frequencies being reflected away from your shirt toward that mirror. Well, when that red frequency reaches the mirror and then comes back out at you, it's the same frequency, which is why your red shirt looks red and not blue or green or something else, because the wave that goes in is exactly like the wave that comes out. It's just moving in a new direction. Another example is an echo. You stand at the edge of a canyon and you shout, and a couple seconds later you hear your sound come back. That's because the sound wave traveled to one side of the canyon, bounced off, and came back. Again, all waves reflect, and you saw a video the other day about a tsunami where there was a reflection of a water wave in the ocean that actually hit the coast of Sri Lanka. They didn't know why, and they figured out it's because the water waves reflected. This law of reflection at the bottom really shouldn't even be an equation. It's really, really simple. The angle of incidence equals the angle of reflection. That just means the way it comes in is the way it goes out. This angle here, if I make a normal, which is a line that is simply perpendicular to the surface of reflection, the angle that is made between the wave and that normal is equal to the wave that's coming out and the normal, right? So it goes in the same way it comes out. And you already know this, like balls bounce off walls like this. Like this, everything bounces and reflects just like this. The angle of incidence, angle it goes in, is the same angle it comes out. So that's reflection. The second one is refraction. You first of all need to know that I'm just going to barely spend a little bit of time on refraction because we can go into a lot of detail on refraction, and we are going to a little bit later when we get to light. But refraction happens when light wave or any waves bend when they cross a boundary between two different media. And that right there is really important. You need to put that in your notes, between two different media. It has to take place when there is a medium change, not just something about the medium. Well, no, there could be something about the medium as well, because a refraction is what's happening when if you're grilling some stuff on a grill, you got some heat rising up, and if you look through that heat, you'll notice the stuff on the other side is real wavy. All that really is refraction due to the heat rising, which increases the pressure in the air, and that pressure changes the medium, which changes the speed of the waves going through it, and it makes everything look funky. So when waves travel through a different medium, or a medium that has some different characteristics, those waves change direction. And we can talk about why that happens later, but you don't need to know that now. You just need to know that waves change direction. So some good examples of this: all lenses. If you have a magnifying glass, if you wear glasses, all of that works because of refraction. We're making the waves, the light waves in that case, bend so that they're doing special things for us. We'll talk about all that later. If you put a spoon or a straw, or in this case, a popsicle stick, in a glass of water, you'll notice that it looks broken or off a little bit. Well, that's because the light waves are bending when they're coming out of the water into the glass and then again into the air. There's a medium change there. And so we have refraction going on. Again, shining a laser through this piece of, looks like acrylic plastic. It's bending here when it goes into the plastic, and it bends again when it comes back out of the plastic. So that's just some decent examples of refraction. Bending of a wave, and again, any wave, when it changes mediums, when the medium changes. We'll talk more in detail about that later. Now, diffraction is really, really similar. You need to know the difference between refraction and diffraction, because diffraction is bending of waves as well. But now, write this down, we do not have a medium change. So medium change with refraction Same medium with diffraction. What happens with diffraction is because of the second law of thermodynamics and waves wanting to simply spread out, when they get to the corner of a barrier like this corner here, they simply don't continue to move in a straight line, but they will spread out past the corner of a barrier. Great example of this is that you can hear someone. If someone was outside my room right now and the door was open, I could hear them even though I couldn't see them and they're not in the doorway talking to me, because the sound waves bend around the corner of that barrier because energy wants to spread out. Here's a good picture of it. You can be on one side of a wall talking to your friend on the other. They don't have to see you because your sound waves bend. Same way with water waves. If you have water waves moving into a barrier here, if there's a small opening in that barrier, the water waves don't continue just straight on the other side. Like, we don't get one small straight line of waves on that side. The waves spread out in both directions. Second law of thermodynamics. All energy wants to spread out. And so that's why that happens. So that's diffraction. Once again, no medium change, right? No medium change here. Same medium, all in air. If this is water at the bottom, water on one side, water on the other, no medium change. It's just around the corner of a barrier. So refraction, medium change, no barriers. Diffraction, no medium change. We're going around the corner of a barrier. Last, we have absorption, which is pretty obvious. Waves get smaller or can go away entirely as they travel into or through a boundary. Depends on what that boundary is made of and what kind of waves we're talking about. Some examples of this: if you have carpet in your home, you'll notice that the sound is more muted. And if you've ever removed that carpet, you're like, wow, it's a lot more echoey in here, because the sound bounces off the concrete a lot easier than it bounces off of carpet. The carpet absorbs those waves. It does not reflect them back, for the same reason that a ball bounces off of concrete a lot easier than the carpet itself. Carpet simply absorbs that energy. Dark colors absorb light. You have a dark shirt on, that means all colors of light are being absorbed into that rather than reflected back out. Soundproofing, if you're in band or choir, you might have a room that has soundproofing to eliminate echoes against the walls, because that can mess up the sound a little bit. But that's absorption. So once again, waves do all four of these things, and there are more things we'll talk about later. Reflection, waves bouncing; refraction, waves bending when there's a new medium; diffraction, waves bending around the corner of a barrier; and absorption, waves getting smaller as they go into an absorptive boundary.